Hi, so we're going to move on to section 2.2, where we're going to talk about sample spaces and the algebra of sets. So this is really where we're going to begin to formalize probability a little more carefully. So we need to introduce some language for talking about random processes. And what we're going to introduce is the following. So we're going to introduce the notion of an experiment. An experiment is going to be something that consists or that can produce sample outcomes. And the whole set of those possible outcomes are going to be the so-called sample space. And then we're going to talk about, define this notion of an event. So these terms, experiment, sample outcome, sample space, and event, have very specific technical meaning within the context of probability that may be a little bit different from their more general meaning. So we're going to discuss what these means. So whenever we're talking about a process that we can talk about probabilities occurring, what we are referring to is like something happening. So, for instance, if I'm talking about, rolling a dice, this is something I can do, and every time I do it, I can have a different number come up. Okay, so that's one thing that can occur. So, whenever we talk about the probability of something happening, this is within the context of a specific, theoretically repeatable process with a set of well-defined possible outcomes. And that is something that we, in this class, are going to call an experiment. So an experiment is a process that produces outcomes. So even though I'm not testing some great scientific theory when I do this, if I roll the die, I can consider that to be an experiment because it's a repeatable process. I can roll it now, I can roll it later, and it has a set of well-defined possible outcomes. So one of the 6 numbers comes up. So, other examples like this. Another experiment could be, I take a deck of cards, shuffle it. And draw one card off the top. So, okay, what did I get? 9 of spades. That is a process that I could theoretically repeat. I could also think of another experiment as being drawing 2 cards. So if I think of the whole process as being taking the deck, shuffling it, and then drawing 2 cards, that produces a well-defined set of outcomes, and I can theoretically repeat that process. So other examples could be if I pick a randomly selected student from Math 465 and measure his or her height. That's a process that I can theoretically repeat. I'm not going to get exactly the same answer every time because I might pick a different student. But it's I can repeat it and it produces a set of well-defined outcomes. So in that case, the outcomes are going to be a number of either centimeters or inches or whatever unit I'm using. Another thing I can think of is the experiment could be live for one more day and see what the weather is like tomorrow. So this is a little bit of a different kind of situation. I have to define that as the experiment if I want to talk about what is the chance of it raining tomorrow. So if I'm talking about what's the chance of it raining tomorrow, then I'm thinking of the experiment as being, waiting one day and seeing what the weather is like, whether or not it's raining. So that is a little bit funny because it's not really possible to repeat it in the same way that I can repeat rolling a dice or selecting a card from a shuffled deck. But this raises some sort of philosophical questions about what is the probability of a process if you can't like actually repeat the experiment so many times. But we think of it as being an experiment because it's a process that I can at least kind of imagine replaying multiple times and being able to have different potentially weather patterns occur with different chances. So that's another example of a type of experiment. Another one could be if I leave work at 5 and drive home and measure how long it takes me to get home. That's an experiment. Theoretically, I can repeat that, and I might take different times to get home depending on different types of conditions. So that's an experiment that's producing a well-defined set of sample outcomes. Okay. Here's another one I had. If I have a list of phone numbers, I can think of an experiment as being call one number and then ask a survey about, I don't know, dental hygiene. So maybe I'll ask, hello, I'm calling from wherever. I would like to know, how many times a day do you brush your teeth? Do you floss every day? Do you use mouthwash? How regularly do you visit a dentist? If I think about the answer of that survey as being a set of well-defined questions, then the outcome of this experiment can be considered. I consider this whole process as being one experiment. So this is theoretically repeatable because I could at least imagine repeating it, choosing a number from random from this list of phone numbers, calling and answering the same questions, and coding up the answers in the same way. So this experiment produces an outcome. The outcome is maybe like the set of answers to that questions, or perhaps like the person didn't answer at all, or didn't pick up, or didn't want to talk to me. So you just have to make sure that your outcomes are well defined. So anyway, the whole point of this is that once we have a well-defined experiment with a set of well-defined sample outcomes, then we can start talking about probabilities related to different occurrences of different outcomes. Okay, so I just put these up on the board here, but I'll now define them. So an experiment, I want to think of this as a theoretically repeatable process that produces outcomes. So now the sample outcome is something that can be produced by an experiment. Okay, so the sample space is the set of all possible outcomes for an experiment. Before I proceed with this, let me just give you a couple of examples. So if I have this simple experiment of taking a single die and rolling it, every time I repeat that process, I produce a different sample outcome. And if you think about that, for this experiment of rolling a dice, the sample space is going to be the set of all possible numbers that can come up. So this is just 1, 2, 3, 4, 5, 6. So that would be the sample space for this very simple experiment of rolling a single die. If I made it a little bit more complicated and say, now I'm not just going to roll a single die, but I'm going to roll 2 die, and I number them or label them different colors. So I have a black die and a red die. I can roll them. Now, every time I produce the experiment, my outcomes don't consist of just a single number, they consist of 2 numbers. So if I order them by saying, okay, I'm going to consider the black die before the red die, this would be the outcome of 5, 1. So in that case, we're rolling 2 die, labeled dice. I could describe the sample space as the set of all ordered pairs of numbers between 1 and 6. So 1, 1, 1, 2, 1, 3, and so on. So I'm not going to list all of these because it would take too long. But if you think about this, like this goes all the way to 6, 6. Okay, so this sample space had 6 elements. If you think about it, this sample space is going to have 36 elements. I could also think of rolling a single die twice as being my experiment. So, sorry, let me back up. I could think of rolling a single die twice as being an experiment. So if I roll it once, maybe I get 3 comes up. Roll it again, 4 comes up. So if you think about it carefully, rolling a single dice sequentially 2 times can have the same sample space as rolling 2 different labeled dice. So just this is just to get you thinking about how the sample space can vary depending on the experiment. Okay, so for the example of measuring height, of a randomly selected Math 465 student, now I'm going to, the sample space is not going to be necessarily a finite set of integers in the same way that rolling the die was, but in theory, it can be a continuous number. So one way I could describe the sample space is just to say, well, maybe I'm not going to put any hard limit on how short or how tall I might expect these students to be. So I'm going to say that I could have the sample space to be all positive numbers. So this is interval notation, the open interval from 0 to infinity. So if I take the measurement in inches, then it's going to produce an outcome that's going to be a number in this space S. So that would be one way of thinking about it. If you wanted to get a little picky, if you wanted to dig into this a little bit more, perhaps I could say, well, this is a finite set of real numbers because there are only 9 students in the class. And so I could think of this as being a list of all 9 of those heights for those students. But it's often more convenient for this just to think of the sample space as being just a positive real number. So this is an important difference. So this kind of sample space here is finite. There are only 6 possibilities. This is still finite. It's bigger, but it's still finite. There are only 36 possibilities. This sample space here is potentially infinite. So, I mean, without measuring every single one of your heights, if I think of measuring this very precisely in inches, your height very precisely in inches, it could be almost any real number, well, within reason, but there's not a discrete set of fixed levels. And if I change this process to be, rather than measuring the height of a randomly selected student in this classroom, and said measure the height of an American, randomly selected American person, then you can see, well, it really makes sense to think of this as a totally continuous set of possibilities. So this is an important distinction. We often have some processes that produce discrete sample outcomes and other types of processes that produce continuous sample outcomes. Okay, maybe another experiment would be I pick a random math 465 student and make him or her do push-ups until they cannot do any more. Okay, so I'd be like, you, drop and give me as many push-ups as you can. And then you do push-ups until your arms give out and you can't do anymore. So here, the sample outcome is the number of push-ups that the student can do. So don't worry, you haven't met me, but I'm not actually a very mean person. I wouldn't do this to you in reality. But what would the sample space be for this experiment? Well, if you think about it, the number of push-ups is going to be an integer, so maybe you can do 0, 1, 2, 3, 4, 5. And kind of in the same way here where I put infinity here, just to say, of course, people are not infinitely large, I just don't want to prejudge like what the top limit could be. You could think of the sample space here as being all possible positive integers. So I could have S equal to all positive, or all non-negative integers, which I could write this way. It's like 0, 1, 2, 3. And if I put dot, dot, dot there, that means I'm not ending this at any particular number. Okay, so that would be the experiment. You know, maybe you over there can do 10 push-ups, you over there are stronger and can do 15 push-ups. Every time I do the experiment, I get a different number because there's some randomness in both in your abilities and also maybe at any particular time there may be some randomness associated with how tired or sleepy you are that might change how many push-ups you can do. So that's a random process that has a sample outcome, sample space that consists of the positive or the non-negative integers. So just this sample space is infinite, theoretically, but is discrete, whereas this sample space is infinite and is also continuous. And this sample space is finite. So that kind of covers the basis of different cardinalities of sample spaces that we might see. So let me give you another example, a little bit fanciful, but I can imagine a situation where I take a mouse and release the mouse in a laboratory. Where there are coordinates on the laboratory. And my question is, the experiment is to record the mouse's position after 15 seconds. So just like, imagining I have a tabletop where I put X and Y coordinates just to be able to identify any position. I let the mouse go, and the mouse, maybe is scared, so freezes for 5 seconds and then runs over here, and then that's where the mouse is after 15 seconds. And so I could record, oh, that's the X position, and that's the Y position of the mouse. So, perhaps, I don't know why you'd want to do this, but it's something that you could think of as being an experiment, probability in the probabilistic sense. So you could theoretically repeat this and ask questions about what the probability of the mouse being in different positions after 15 seconds would be. Okay, so what would the sample space for this would be is ordered pairs of positions, so where x and y are real numbers. Hold on a second.